Yeah, now we are live now. Hello, everyone, dear colleagues, friends, and members of HVPS. You are very welcome to attend this HVPS Young Professional Virtual University Live Visit. So this time we have this Cardiff University. The speakers are Dr. Jinlei Chen and Dr. Wei Gan. Today we are going to know the knowledge and information from this electronic department of Cardiff University, and then we will have this live visit from Dr. Jinlei. He will present his research work as well. So the aim of this event is to bring all these young professionals and colleagues to know these famous universities live for electrical engineering, and to encourage all these students to apply these research positions and to do some research activities. We can also broadcast of the information of these universities and to attract talents globally. We can also bridge these connections between different institutions to have this more international collaboration, to provide these chances for networking and to build up these collaborations. So today we have this Dr. Gan Wei. He will present the knowledge of this Cardiff University. I think now I will stop sharing my. Now we can. Now you can present your
Okay.
slides.
Okay. Wait a minute. Let me share my screen.
And you can, yeah, sorry. First of all, I can introduce myself. I forgot to do that. I'm Gan Li from Technical University of Denmark, and I'm currently an associate professor at DTU, and I'm the academic and sub-faculty coordinator of HVPS Young Professionals. And Dr. Wei Gan is a postdoc at Cardiff University doing his postdoc research. And then now over to you. You can first introduce yourself. Yeah.
Okay. Yeah. Thank you. Thank you. I will share my screen first. Okay. So can you see my screen? Sorry. Prophet Lee, can you see my screen?
Yes.
Yes. Now I already started. You can.
Okay. Okay. So I can get started. Okay. So first, I would say thank you to Professor Lee. Thank you for inviting me to providing such a opportunity. And then thank you for everyone who attended this webinar. And firstly, I would like to introduce myself. After graduation from Cardiff University in China, I came to the UK, Cardiff University, a very nice university, to conduct research as a research associate, and have been there for about 2 years. So firstly, and then I would be very glad to introduce something about our lab, including the HVDC PE research group, which is the main scope of our today's presentation. And then actually the HVDC PE research group is part of the CGRAS, which is the bigger group we all belong to. And today I will introduce both of them. And to give you some more background, I would start from the Cardiff first. The Cardiff is the capital and the largest city in Wales, and also it's also one of the one of the top 10 largest city in the UK. When we go back to history, in the 19th century, it was a major part for the transport. But these days, industry, shipbuilding, machine manufacture, and textile, and so on, have recessed. Right now, Cardiff usually is a bilingual English and Welsh city. And also from these figures, you can see that Cardiff is a very beautiful and quiet and nice city. And I'm in President Cardiff to welcome all of you to have visit or have the academic visit in Cardiff. And then let's move forward to our Cardiff University. Cardiff University is the most important university in Wales, and also it's also one of the Rosso group of university, which consists 24 leading UK universities, other universities in the Rosso group like the Oxford and the Cambridge University, also Birmingham, and so on. So Cardiff is also a member of all of the well-known universities in the UK. And in the latest REF, which is a very important research excellence framework assessment in the UK, our Cardiff University was ranked top 10 amongst all the UK universities. And also, when we focus on the research power, the research power of our university ranked 14th in the UK. And our School of Engineering is even strong in our universities. It's one of the university's largest schools, and also it has a staff total around 255, which includes about 90 academic. And then the total students are even more than 1,500. Mostly, we have 1,200 undergraduate students and the master and engineering students. The other students may include MSc, postgraduate, PhD, and since our research performance is really good, and annually we will get funding over £20 million. Okay, let's move on from Cardiff University to our research lab. Our research lab, the full name is the Center for Integrated Renewable Generation and Supply, which can be simply called CREX. CREX lab is funded by several well-known professors, and the most popular one is Professor Jack Nickens, who is an HVDC fellow and also the academic of the Royal Academy in the UK. And our CREX focus on many areas associated with energy. And we have several research groups, which include the smart grid group, multi-vector energy, and the HVDC and power electronics. The third one is what the Dr. Jin Lei are going to have a detailed presentation associated with this topic. And also we have have a wide range research topics from power system control, integration renewables, and to the power electronics. And then let's move further from CREX to today's main topic, the HVDC and power electronics groups. The HVDC is the high voltage direct current and power electronics, which is a quite new technology to deal with the integration of renewable, and also to have a focus on developing technology for MTDC grid and offshore wind networks, and also to have its impact on onshore transmission networks. And in our HVDC and power electronics group itself, we have more than 15. Today, the number will be even larger. We have such a big number of academics and PhD students, and also postdocs, and some visiting academics from well-known universities overseas. And here, this figure, you can see find experimental area we usually work in. And next, I'm going to introduce some important or the equipment we usually use in the experiment. So firstly, I will introduce the wind generators. Here, the wind generators are used to simulate the real operation characteristics of wind farms, of wind turbines. And then this is the generation. And then we can use the converters, the VC. This is voltage source, the converter, to do some conversion from the wind generators. And then the fourth one is the DC circuits and is circuit breakers to do some circuit control and break of the whole systems. And in the bottom, we have another 4 figures, which are composed of the power amplifier, RTDS, and another power amplifier. Here, usually we use RTDS, which can provide real-time digital simulation as the control signal to the power amplifier, and to do some real simulations which can reflect the character of the real power systems. And here, for these 2 figures, you can use the RTDS to provide the signals. And for the power amplifier 2 and 3, this is another type of power amplifier which can use the OPPO RT to provide control signals, like this part is the output RT to provide the control signals. And then we have more detailed equipment such as AC converter, and inside they can randomly use this competence to control the topology of the AC DC devices. And this one is for the MVDC test rig. In the last page, we usually introduce the equipment for the HVDC. And here we have some devices for the MVDC, which is a medium voltage direct current. And here we have another two equipments like the TCSC. TCSC is the controlled the series capacitor, which is seems like the capacitor bank to provide the reactive control. And then this is the PMCG. It's something like the scenario generator. This is the most used equipment in our lab. And then, regarding our HVDC and PE group, usually we have specific research topics from the control system design and the integration of offshore wind farms, and something like the offshore AC hub, as well as a multi-terminal LCC HVDC grid, and also which includes something like the damping of SSR and the frequency support to AC grid from the DC grids. You can smartly control the DC part using the power electric devices to provide some support to the AC grid, such as a frequency support. And also, it's similar, you can do something from the voltage control. And also, we can use the flexible DC power flow control in meshed DC grids to better management our DC grids. And also, if we go more detail, we can have an investigation of the DC investigators. So actually, generally, we have a wide research related to power electric, from the devices, switches itself, and also to the power system control. Okay, just a rough background introduction to our lab, and also I would very welcome if any of you would have a visit to Cardiff and also to our Cardiff University to have a academic visit or just have a tour visit. Okay, thank you for your time.
Okay, thank you very much, Dr. Wigan, and it's very informative, and we have learned about this Cardiff University's group. Actually, previously I was there. I'm very familiar with these devices there. And now I think we can welcome Jinlei Chen to present his work, and he is more Poltronics guy and working in the lab in the past 4 years, right? And he knows a lot about these devices and these toys. I think now you can unmute yourself and start to present your work. Over to you, Dr. Chen.
Okay, thank you. I will share my screen now. Can anybody see my screen now?
Yes, now we can see your screen.
Okay. Thanks, Prof. Gunley, for inviting me to this virtual live visit forum, and so that I can share my lab work with all of you. And thank you for the interesting introduction from Dr. Wei Gan. So let us move to the lab work of mine. So the topic today is active control of medium voltage through level.
Sorry, Jinlei, I think you can make it full screen.
Okay. So.
Okay, yeah, good.
Okay, so the topic is the active control of medium voltage three-level neutral point collapsed converters. My name is Jinlei Chen. I'm now a postdoc in Cardiff University in UK, and my research interest is about the control of power electronics, especially in the medium voltage application, and also the modeling of power semiconductors such as silicon carbide devices. So before going into the formal topics, let me briefly introduce the background of my lab work. So my lab work is based on the Angles DC project, which is the first medium voltage DC project in UK. And as shown in the first map, there is the Anglesey Island in the neighbor with the North Wales, the mainland of North Wales, and there are many renewable energies such as wind powers that should be collected and transmitted to the mainland of North Wales. So previously, the AC circuit was adopted for the power transmission. However, the thermal and voltage limits have been reached. So to improve the volume of the energy transmission, the AC circuit has been adapted for MVDC operation. And by using the MVDC operation, the power capacity has been increased from around 20 megawatt to around 30 megawatt. So the power capacity has been highly increased. And in this system, a novel cascaded three-level NPC converter has been adopted for the first time. As shown here, for this type of converter, there are 12 submodules cascaded together in each converter station. We can see that the DC sides of the submodules are connected in series connection, while the AC sides are in parallel connection with using the isolation transformers. So there are some challenges listed here. First, we need a prototype to assess the performance of this system, because in the previous study, most works have been conducted in the computer-based simulation in the desktop and is inadequately to assess the performance of the system. And also, due to the series connection topology, the voltage and power imbalance between the submodules may appear, and it may cause the system instability. Besides, the multiple submodules also will result in the reliability issue. For example, if the thermal stresses are unequally shared, distributed between the submodules, some submodules will encounter premature aging, and it will decrease the overall lifetime of the system. So in the first stage, we developed a laboratory-scaled MVDC testbed. This is the hardware configurations of the MVDC testbed. In the first picture, there is a back-to-back three-level NPC converter stations. And we omitted the DC impedance and just connect them together. And in the second picture, we connected the boxes to the power supply. This power supply adopts the power amplifier. This is a controllable power source. It can be controlled by the OPRT to mimic different conditions of AC grid. And in the left corner figure, I put the internal structure of each cascaded three-level NPC converter here. So all of the submodules are put in the top, and in the bottom there are two isolation transformers, and also there is another main controller at the bottom too. It's used to communicate with the submodules to coordinate all the local controllers. And for each local controllers, is shown here. It includes three parts. The first is the power supplies for the PCB board, and the other is the DSP board. Is a microcontroller, and also there are three-phase gate drivers to drive the IGBT power modules, and also there are protection circuit and the communication circuits. The communication circuit is based on the RS485 cable using the Modbus protocol. So in line with the HV standard, we developed the suitable hierarchical control structure for this type of converter. It includes several control layers. The application control layers is performed in the main controller, it can operate it under several control modes, such as the droop control, the power control, and the DC voltage control. And also, the command is calculated in the main controller as well. The command and the references are sent from the main controller to the sub-module controllers. And the sub-module controllers perform the current control and the PWM modulation. So this is a basic control structure of this converter. And one feature of this test bed is that it has a similar per unit values as those employed in the real system. So we can see in the table that either the power rating or the passive components have the similar per unit values as the real system. And I conducted the comparison tests between the simulation and experiment. And we can see that they are in good agreement, although there is a slight mismatch in the oscillations. So it can basically reflect the performance of the real system. And for reference, I record a short demo of the laboratory demonstration. So I will show it to you. This is a setup of the experimental platform. It includes the power amplifier and the two converter stations. So before running this machine, we need to firstly power up the circuit of the controller circuit. So here, the red light indicated that the controller circuit has been enabled. After the controller circuit is enabled, we can then enable the main circuit. So, sorry. Let's go back to where we are. So the green button is turned on. That means the main power supply is connected with the converter station. So the DC voltage has been increased. That means the DC capacitance has been charged from the anti-parallel diodes of the converter. We can see there is a step change of the DC voltage. So then we could enable the DC voltage control to make the DC voltage reach the given reference. So I use the ramp function to slowly increase the DC voltage to the reference. After the DC voltage is stabilized, the power control can be enabled afterwards. So the right curves indicates the AC current. So only one converter station is enabled, so it's operated at the StatCom operation. So only the reactive power is shown here. We gave different set points of the reactive power, so it can change and trace our given reference. So in the end, we disable the power and it decreased to 0. And after finish the demonstration, we disable all of the controllers and open the relays in the converter station. So we can see that the DC voltage slowly decrease is due to the discharge of the DC capacitance through the resistors. And then we shut down the system and let's go back to the initial stage. So that's the basic demonstration of this startup and shutdown and running of this machine. Okay. So based on this testbed, I conducted the stability-related DC voltage balance control. So for this type of converter, one converter station is with DC voltage control, while the other station with power control. For the power control side, the DC voltage imbalance may occur due to the cascaded topology. So this will influence the system instability. Also, the system requires communication between the submodules and the main controller. Upon loss of the communication, the system will also face instability. So to address this challenge, I firstly analyzes the DC voltage imbalance through the circuit-based analysis and the model-based analysis. So we can see that in the model-based analysis, there is a dominant pole in the right half S-plane, which implies that the system is unstable. So afterwards, I presented the voltage balance control, combining the methods with communication and without communication. So the PI-based control is with communication, and it's taken as the first choice due to its precise voltage balancing control performance, and also is decoupled from the power controller. However, upon loss of this communication, the PI-based control is out of use because it's dependent on the communication. So upon the loss of communication, it will switch to the droop-based balancing controller, and to ensure the continuous operation of the system. And I also developed the small signal model for the system stability analysis and the controller parameter tuning. This is an experimental validation. And first, without using the voltage balance control, we can see that the DC voltages of the submodules will diverge as the time goes, and which implies the system instability. And after using the PI-based voltage balancing control and the droop-based balance control, the DC voltages of submodules can be balanced effectively, and system is stable. And the last page shows the transition between different control modes. We can see there that the transition is smoothly, and there is not oscillations in the transition between the different control modes. And afterwards, to enhance the system reliability, I also developed the active thermal sharing control. So first, the system reliability is highly related to the thermal stresses of the power modules. We can see that in each power modules, due to the package, the thermal stresses may be high in some modules, and the high overheating of the submodules will cause the bond wear lift off and crack of solder point, so that some modules may be damaged due to the high thermal stresses, and the reliability of the system will be decreased. So to balance the thermal stresses among some modules, I superposed a thermal controller on the traditional DC voltage controller. We can see that the high-level main controller collects all the junction temperatures from submodules, and then set the mean temperature of submodules as a reference to submodule controllers. And there are two thermal PI regulators, and one is to regulate the reactive power of submodule, and another one is to regulate the active power of submodule. So they jointly redistribute the thermal stresses among submodules, and by using the thermal sharing control method, the thermal stresses are equally shared by submodules, and they have the same lifetime. So this is a comparison test of the thermal control strategies. So in first one, the junction temperatures of some modules are different due to the unequal cooling system conditions. The cooling fine of some module 1 is controlled at 60% of rated speed, and the others at the normal 100 rated speed. So we can see that there is a temperature difference of 8 centigrade between these submodules. And after enabling the active thermal sharing control, the temperature difference can be effectively balanced. And we can see that the load of each submodule is different. So I draw some conclusions here. Firstly, we developed a laboratory scale HVDC test bed based on the AngoDC project to assess the system performance. To enhance the system stability, we developed 2 types of DC voltage balancing control methods. And furthermore, to enhance the system reliability related to the junction temperatures, I developed the active thermal sharing control methods. And our future work will be focused on the modular and the compact design using the wide band gap semiconductors, such as the silicon carbide devices, because as you know, the silicon carbide devices have many advantages over the traditional silicon IGBTs. So they can highly improve the system power density and efficiency, because the passive filters such as the inductance and capacitance can be highly reduced, and the volume can be reduced as well. So that's the objective in our future. So thank you for your listening, and thank you for listening. Thank you.
Okay, thank you very much, Dr. Chen. It's very interesting, and I can see you already have this very fruitful results after your PhD study. Before I came to DTU, you are still PhD student. Maybe I can ask you a question about your research. Yeah. So this AngoDC project is now commissioning, right? Do you know any other project is using the same topology of your converter?
In my knowledge, I didn't see any other, the similar converter topologies in the real application.
Okay.
Yeah.
And how about your paper? You have published some papers. Did you see anyone cite your research paper? Maybe they are working on the same thing. I mean.
Yeah, but they focus on different topologies, and because most studies are focused on the MMC topology.
Yeah.
But this topology has a smaller footprint and lower cost than those, but it has not been fully explored. So I think it's a promising method, maybe in the future, I think. Yeah.
Okay. And you are still working on this converter configuration?
Yeah, we try to replace the traditional semiconductors with such as silicon carbide devices to improve the performance.
So this is your ongoing postdoc research?
I think so, yeah.
Oh, okay. Excellent, super. I think we didn't collect any comments or suggestions, nothing from the floor. So I think if we have nothing, we can close today's webinar. Yeah, let me check. Someone post here. Thanks for interesting lecture. My question is, what about the role of voltage and the current sensor for your work? What is the role of your current and voltage sensor in your work?
So the current sensor is stored on the AC side of each converter, of each submodule for the current closed loop control, and the DC voltage is sensed from the DC side of the converter for the DC voltage control. So, and also for the protection. So I am not, if my answer makes sense.
I don't know if safe, this audience is safe. If safe, the question is answered or not. Or if you have questions, you can email to Dr. Chen. Yeah. Okay. Okay, so I think we can close today's very outstanding event today. And thank you for your time, preparation, and your effort on preparing all these slides and the live demonstration, and also the information from Dr. Wei-Gan. And thank you so much for today. And if you have any questions, please feel free to, you can easily Google, find them. And they have their personal page at Cardiff University's website, and contact them to have some detailed answers and communication. So thank you of all, and we can see you next time for, I think it will be next time will be in August. So we have another university, and we will broadcast today, like today, and have this information in advance at HVPS Young Professionals platform. Okay, thank you very much. See you next time. Bye bye. I think
See you.
Thank you. Bye-bye.
Bye bye.
Bye bye.
Bye.